So now we're going to talk about systems design. Now we know what kind of mission we're going to do, we know how many sensors, we know how many UAVs, we can go start designing the vehicles themselves. This is the highest point selection in the report, as we talked about, and you must tell the judges not just what, but also why on all design decisions. And you see in the orange box on the side the detailed outline for this. In every one of these areas, answer the questions. Even if you didn't do a lot of work in any one of those, go in, tell them what you did, what you didn't do, and why. So let's start with the systems design. Really, the first two areas you're going to be looking at is conceptual design. Conceptual design is really your first guess. You're just looking at where do you want to start with some of the key design parameters. And this is just hand-drawn or 2D computer drawings. You're not starting all the 3D CAD work at this point. This is very quick. You're just getting a lot of ideas out on the table. Limited analysis to eliminate some ideas that just don't work. And then you pick the best ideas, the best concepts that you looked at to take to the next step, which is preliminary design. In preliminary design, you do more detailed analysis. You start running the tools that were supplied through the Real-World Design Challenge. You do the vehicle sizing and synthesis. You first simple CAD, computer-aided design, vehicle layout. And then finally you down select to your final vehicle parameters when then you go do your detailed design. So we're going to talk mostly about concept and early preliminary design today. So as we look at our design decisions from our mission plan, we had our sensor selection, our number of UAVs, our design mission. All those decisions flow right into our vehicle design. Some of the key decisions we have to make there are wing loading, power loading, the engine selection, the geometry of our wing, the airfoil selection, the tail geometry, the fuselage geometry, our weight estimation, and material selection. So we're going to talk a little about that. The mission payload is very important. If you look at the total vehicle weight, we define that as the empty weight plus the useful load. Empty weight is the airframe weight, the structure, all those things, plus the engine weight, plus the basic control systems weight, the ailerons, the vertical tail, the elevator on the horizontal tail, all those things that are basic to making the vehicle fly. And then the useful load is the payload weight, the sensors, the radios that go along with it, all those things, plus the fuel weight or any batteries or anything you need on there. Time aloft is restricted by this 55-pound UAV weight limit. You can only put so many sensors and so much fuel on board and be able to keep that vehicle in the air. And then the payload weight versus the fuel weight versus endurance. This is the trade-off you're going to look at. You can trade payload for fuel to get more endurance. So this is one of the things you have to look at. As I said, if you go with a very small, lightweight sensor to start with, you can put lots of fuel on the vehicle and stay aloft for a very long time. If you want very heavy sensor or multiple sensors, you can't put very much fuel on board, and you're going to have a very short time aloft. This is your trade-off. So if we look at some of the starting vehicle parameters, wing loading, this is the ratio of the max weight of the vehicle to the wing area. This gives us a sense of how much of the weight the wing has to carry. And this is really sets your stall speed. And in the orange box we said the wing loading, W over S, is equal to 1/2 rho, that's air density, velocity squared, CL. CL stands for the lift coefficient of the vehicle. If you look at vehicles in this class, the wing loading ranges anywhere from 1 to 4 pounds per square foot for this class of vehicles. So if in your quick analysis you start getting loadings of 10, 15, 20 or anything like that, you know right off the bat you're out of range. You should be in this 1 to 4 range or somewhere around in there. Power loading, that's the ratio of the max weight of the vehicle to the max engine power. You must have enough power to offset the aerodynamic drag of the vehicle for cruise, plus extra power for that quick takeoff. Remember, you have to get off the ground and up to 50 feet altitude and 300 feet. For this kind of vehicle, the range is anywhere from 12 to 16 pounds per horsepower. So that's very important. Again, if you initial rough numbers, you're out of that range, you should take another look at it. The weight fraction, we talk about this in designing vehicles, is the ratio of the empty weight to the max takeoff weight. And the range for most of these vehicles is anywhere from 0.45 to 0.55. Roughly about half the weight of the vehicle is just structure, engine, control systems, and the other half of the weight is fuel and sensors, and that's very important. And for this first cut, you just use simple ratios for your concept design, and you can refine that later with more detailed analysis. So we start looking at our wing geometry. Some of the key areas you need to look at there are taper ratio. That's the ratio of the tip chord to root chord. And you see the drawings on the right side there. Non-tapered wings, they look like a big Hershey bar. They're very easy to build. All the wing ribs, all the structure is the same at the root as the tip. You can build a no-taper wing very, very quickly. Tapered wings, however, are better aerodynamically, but they're harder to build because every one of those wing ribs on one side is different. So you mirror them on the other side, so you're making two of each rib, but you're making lots of different wing ribs, the structure in there, and it's harder to build. If you look at taper ratios for these kinds of vehicles, 1.0, meaning no taper, to 0.6 is traditional for small aircraft. I would recommend starting with no taper. You'll see a lot of UAVs out there with no taper wings because they're easy to build, light, and very low cost. Aspect ratio, that is the span squared divided by the wing area. It's roughly a way to describe the fineness of the wing. And you see in the pictures to the right, the high aspect ratio wing has a lot of wingspan, it's very fine. It reduces your cruise drag, but it has a higher structural weight than a low aspect ratio wing. In this kind of vehicle, because we're flying fairly short distances, we're flying fairly slow, the aspect ratio has little effect on these vehicles, and the range of numbers here are anywhere from 4 to 8. The last thing on the wing geometry is the airfoils. You need to pick one with a high lift coefficient that gives you good lift at low speed. Remember, we're not flying very far, we're not flying very fast. You can't fly fast because you'll fly over your target with your sensor and possibly miss it. So you have to have a good CL here. One thing for you to remember is that when you pick your airfoil and you have your lift coefficient, let's say you pick an airfoil with a 1.6 maximum lift coefficient, that is not your vehicle coefficient because you have losses at the wingtips and things like that. Your vehicle lift, which is C capital L, what you normally use, would be about 80% of the maximum lift coefficient of your wing section. So just remember that. If you looked at fuselage geometry, the fuselage is there to carry all these items. It has the engine in it, it has the sensors, the radios, the batteries, the fuel, all those things. And you see a little CAD drawing of a very simple UAV there with a little wireframe fuselage. So you have to put all those things in this fuselage. Some of the common sense rules for this is make the fuselage just big enough to carry the things that you've defined, sensors, radios, batteries, fuel. Don't put a lot of extra space in there because that extra space costs you weight and drag. You want to minimize weight and drag. Plus, for most of these vehicles, your tails are going to be mounted on the fuselage, so you need the fuselage to be long enough to give a good lever arm for your aerodynamic tails. So a rough rule of thumb is that your fuselage should be anywhere from half to 1.0 of wingspan. So if you have a 14-foot wingspan, your fuselage should be anywhere from 7 feet long to 14 feet long to give you enough arm for your vertical tails and your horizontal tails. Tail geometry. The airfoils for the tails are usually symmetrical. They have no camber in them. So that, remember that you'll probably pick a NACA 00, 15, or 16 would be in that range for this tail. And the tail size is set by some historical data that we call geometric tail volume ratio. And I give you the formulas here for horizontal tail volume and vertical tail volume, where S is the area of the component, the wing, horizontal and vertical. You see SH is the area of the horizontal, and SW is wing, and SV is the area of the vertical tail. L is the length of the arm from your wing to the tail. Remember, you have to have that arm there. MAC is the mean aerodynamic chord, and B is the wingspan. So you can use those equations to come up with values for this. The tail volume coefficient normally for the horizontal tail is anywhere from 0.3 to 0.7. That gives good controllability for vehicles. And for the vertical tail, it's 0.03 to 0.07. You can feed those into the equations, and if you know your arm, you can then pop out what the area of your tail should be. And you see the pictures as a conventional tail where you have a conventional horizontal and a vertical tail on the aft part of the fuselage. A lot of UAVs combine those into a V-tail. So if you have a V-tail, you have to look at how much of that area is projected into the horizontal and projected into the vertical plane. My suggestion on this is that you go with a very conventional tail on this as a starting point. It makes the analysis much easier. Weight estimation. At this point, it's really as simple as the empty weight to the maximum weight ratio. You can start with historical data, the table on the right side of the chart for small aircraft. This is the small light sport aircraft, because there's not a lot of information out there publicly on UAVs. But if you look at the small manned aircraft, that ratio of empty weight to max weight ranges anywhere from 0.49 to 0.64. So we gave you a range earlier, about half, or 0.55 of the weight of the vehicle is going to be in the structure and all those things. And you can refine this weight breakdown later as the design becomes more detailed. But for this initial run, you can use the weight fraction. Engine selection. You've been given a series of engines for this challenge in the detailed document. It gives you the power, the installed weight, and the fuel consumption of it. So how do you pick that first engine? Well, you pick the best fit to those initial design values we've been picking up, and you want a good mid-range power loading of 14 horsepower or pounds per horsepower. And that's a good place to just start your analysis, and then as you do more analysis, you can change the engine if you need more or less power. Now, we've got to talk about electric versus gas, because you're given both gas engines and electric engines. Electric is great. It's quieter, and that's why a lot of RC airplanes now are electric, because it causes less community noise. But is that a consideration for this mission? I'll leave that question with you. Also, electrics, you must have multiple battery packs, because it takes a long time to charge these batteries. So if you land your electric airplane, you have to put another battery pack in, so you have to have in your cost model all these battery packs, and have enough battery packs to cover the whole time you need to be aloft. And you also have access to power to be able to recharge things. Gas is more flexible. There's a lot more of it around. You get quicker turnaround times because you can just pour a couple of gallons of fuel into the UAV very quickly. It is noisy, less environmentally friendly, but again, those items aren't in the rubric for this. You won't get any extra points in your scoring by being environmentally friendly. Just a note there. So if we look at aircraft sizing, and we've given you a little drawing here of what aircraft sizing is about. We start from the left. We start with historical data in the little green box. We look at what are the values that you normally use for aircraft design. Then we take our first guess at the design parameters. What is the wing loading? What is the power loading? What is the wing geometry? All those things. And we create our geometry. From that geometry, we do an aerodynamic analysis to estimate what the drag coefficient is of the vehicle. And then finally, a first guess at the weight of the vehicle. Then we run our mission and performance analysis to determine, we fly this vehicle and determine how much fuel it burns. Then we look at that and say, did this meet the requirements? Yes or no? If it's no, we go back, revise the design parameters, go back through the analysis, and we do this circle many times until we get a vehicle that actually is feasible, it works. And we call that a sized concept, that green box down at the bottom right-hand side. Is that the size concept is not necessarily the best one, it's simply one that is physically feasible. It actually will work. You have to do some trade studies to determine the best combination of design parameters to be able to meet the mission.